Welcome to the AbsInt Videocast for the October release 1910 for the binary level analyzers. My name is Christian Humbert and I'm going to present the latest features of StackAnalyzer, aiT, WCT Analyzer, TimeWeaver, TimingProfiler and the ValueAnalyzer add-on. Here's an overview of the new features in the 1910 release. And I'd like to get started with the improvements and changes in the graphical user interface. The first new feature that I'd like to present is the mass edit feature. And for that, I've prepared a small analysis project with these analysis items here. And if you would like to change now properties of more than one analysis item, so common properties, you can multi-select them. Like in this example, I have here an aiT analysis for the 10 millisecond task, a TimingProfiler, and a StackAnalyzer analysis, all of the same 10 millisecond task. And now I can multi-select them, use the context menu, and click on Edit Selected Analysis. Then a new dialog box will appear, allowing you to change some common attributes. So for instance, we could decide to provide or introduce a new local report file for all those three analyses. So we could click here to report file and make usage of that placeholder, which is like this here. And we can put a report suffix and use this extension txt. And if I click on OK now, we see that for every analysis here, we have a new local report file specified, depending on the original ID name. That is the new mass edit feature. The next change in the graphical user interface affects the TimeWeaver analysis only. Instead of specifying the input trace files locally at every TimeWeaver analysis item, the user now specifies the input trace files on a global level on the setup files in the section trace files. And by the way, we have also separated the input and the output file references in the setup files view here. The last improvement is regarding annotation hints or proposals, and for that I'd like to show an analysis that issues a warning, like in this 1 millisecond task analysis. If I'm going to start that, we will have here a warning about an unresolved computed call problem. And as you know, you can usually use the context menu out of that warning and say add annotation, ICE annotation. This has been changed now to copy ICE annotation, and the effect is that the suggested annotation, the annotation hint, will no longer be directly written to the local ICE file, but placed to the paste buffer, to the clipboard. So by clicking on that, you see a small confirmation window, and it tells you that this annotation hint has been copied to the clipboard. The same, by the way, is also working if you produce the annotation hint out of the graph. So if you go here to the routine node where an annotation proposal is available, you can click to that proposal, and again the annotation will be copied to the clipboard. And then it depends, or it's up to you. You can go to either the local ICE file, paste it here, or of course go to the global ICE file and paste it here. It's up to you. This concludes the GUI related changes. Now let's continue with the TimeWeaver specific improvements. There is a new TimeWeaver specific option to select under Setup Timing Analysis. It's called Perform Value Analysis, and you can disable that option, which will speed up the analysis in general, but also reduce the analysis precision in general. So let's see what happens if I start a TimeWeaver analysis with a disabled value analysis option. If you unfold the control flow and value analysis step, you see directly that the value analysis step has been skipped. All the other phases will be available, of course. For the next feature, I'm going to open the statistics, and especially the trace segments, but statistics. And here, as you know, you can select a specific trace segment, and by double-clicking the corresponding distribution graph for the timings that have been extracted over all trace input files are visualized. And now, in this new release version, you can do a mouse over on such a timestamp, and you will not only get the timing information, but also the information from which original trace file this time information has been extracted. This can be a valuable information on how to reconstruct the corresponding measurement scenario. And this information from the tooltip can also be copied to the clipboard, as you can see. For the next feature, assume that you would like to perform TimeWeaver WCT analysis for the very same task, but under different analysis assumptions. So that is, by the way, what people call task mode analysis. And in my example, I have here two different TimeWeaver analysis items for the very same task, the 10 millisecond task. But in the first item, I have a generic analysis, so especially I do not provide any additional restriction on some global variables. But in the second item, I'm going to restrict the value ranges of certain global variables, and that improved my WCT estimated bound a slightly bit. As you can see, in this generic mode, I had 110 microseconds, and in the restricted version, I have just 107 microseconds. Now, in both items, in both analysis situations, I had to process or follow the entire tool chain, beginning from the control flow reconstruction, the decoding step, and the value analysis, but also the path analysis, the extraction of the timing information and the processing of the trace input files, and the path analysis itself. So in both cases, we had especially to perform the processing of the trace data and the extracting of the timing information. And you can imagine that in real life projects where you have gigabytes of trace data, this can last very long. And since we are processing the very same trace information for the same task entry point here, in both cases, well, we could get rid of this trace processing and extraction step by the new feature which we are introducing in release 1910. It's called trace dependency feature. And I'm going to show how this works. So you could turn the first 10 millisecond task analysis, mode 1 here, into the base analysis, let's say, by producing an output trace file. It's called task 10 millisecond.traval. You can choose your name, by the way. And as soon as you've provided such an output trace file for this processed intermediate trace file, then you can go to the next analysis item of the same entry point and click on the trace dependency here. Now that we have produced that traval file in the first mode, we can select the trace dependency here. And by clicking on OK, you see that now the mode 2 analysis is depending on the mode 1 of the same 10 millisecond task. And the effect is that if I'm going to restart this analysis, it will ask me if I can reuse the existing results from the computation of the mode 1 analysis, and especially the Travail file data, and that we do not have to reprocess the trace data and extract the timing information. As you can see, this step has been skipped, and as I said, this can save a lot of time since this trace processing step can last very long. The next category I'd like to give an overview on are the improvements in the interactive value analysis add-on. For that, I'd like to perform an interactive stack analysis in this case by clicking on the play button with a dot. Note that you need the ValueAnalyzer add-on for this feature I'm going to present. So the analysis has been performed and I can open the resulting graph. So let me make that graph a bit bigger. And if I, for instance, go into the routine node proc7, double click on that, double click on the basic blocks to see the instruction level, and let's assume I'm interested in finding out what this load instruction exactly performs or computes. So let me use the context menu here and click on Show Value Analysis Results to investigate the value analysis data flow information. And what you can see is that for this proc7, we have here in this case exactly 3 different contexts, calling contexts. So from basically 3 different sites, we are calling proc7. And as you can see, depending on the context, we have different information we are loading from the memory. In this case, the value 2 is loaded. In this case, the value 10 and 6. So assume further that this context is interesting for me. So where I came over proc1 to proc3 to proc7. Now you can set this context to be the active context via the context menu. You can say here set active context, and this has been marked now. If I go back to the graph, that's quite interesting. You can now go to, for instance, to the start node and say I'd like to follow back to my caller, and in the previous release you only had the go to caller option and you had to remember now the correct context. Starting from this release on, we introduce also the go to caller for the currently set active context, and you directly jump to the corresponding context. And by the way, this also holds for the go-to target, since our context is still marked as being active here. I can also go here, and if I open a different instruction, I'm still in the actively set context here, where I can investigate the data flow information. So we think that is a very convenient way to follow the data flow information beyond the scope of different routine contexts. The last topic I'd like to discuss today are the AIS2 annotation improvements. And here we have introduced so-called portable source code references by this release. So whenever you want to provide annotations in the external AIS file, you have to refer to usually to program points related to the binary. And you can do that by using an absolute instruction address, or for instance also byte relative address. This is of course not optimal, since these addresses, the absolute or relative addresses, may change when you do recompile. Therefore it's much better to use symbolic program points like this here, R computed 1, it's the first computed call or branch in routine R. But sometimes, due to code holes or similar, these symbolic program points are not available, and then you have to fall back to byte relative addressing. Instead of using that, you can also, of course, refer to the source code module and the source code lines that is also listed in the warning you're going to address with your annotation. Of course, only provided that you have compiled the binary with 12 debug information. So you could, instead of R here 42 bytes offsets, if you had a source code reference to here this module.c file line 12, you can also use this syntax. But as you can imagine, if you have here a complex path to that module, and if this path is, for instance, specific to your concrete environment, this is also not very flexible or robust, or even portable to other environments. And therefore we thought we could improve that here by introducing or allowing to place the match functor within such a source code reference. And we did that by this release. So instead of annotating here source and then the entire path or a string to that module C file, you can also now make usage of the match functor. In this case, you could match anything before the backslash to module.c in order to be portable and independent on the concrete path to the module. Next are the value set comprehensions. This is very similar to the Python list comprehension feature. We introduce a new expression in the AIS2 annotations. It looks like this. Let me make an example to explain it in more detail. Assume you want to introduce a value partitioning, for instance, and you would like to partition over an index variable that has values from 0 to 255. So far, you really had to write manually a set of all these individual numbers from 0 to 255, and there was no abbreviation for it. Now that we have the value set comprehension, you can use that compact expression, and it would, like in this example, it would like this, look like this. It's just referring to variable I, which we are defining here, and we let run that variable I simply from 0 to 255. Of course, you could also have a more complex sub-expression here. You could, for instance, multiply that variable I with, let's say, 2, and then you would start counting all even numbers from 0 to 512. Last but not least, we have extended the mem functor. And instead of referring to the very same complex area annotation within the address and the with operator, so you basically had to refer it here twice to annotate the content of that complex area. Now the mem functor itself directly understands complex area annotations and yes, extracts the address and the width automatically out of the one complex memory area specification. This concludes my presentation on a selected set of the latest features for release 1910 of the binary level analyzers. Of course, there are many more to find on our webpage, absint.com/release notes. Please have a look if you're interested. Thank you very much for your interest in today's videocast. If you have any questions, please feel free to contact us via support@absint.com. Thank you very much. Take care. Bye bye.